Welcome to a fascinating discussion of standard deviation and percent error, your two most common laboratory evaluations in a freshman chemistry lab. Accuracy is how close a measurement is to an accepted value. Now, the classic way of talking about accuracy is to do it in terms of a target. Everybody's either shot at a target or knows somebody who has, or at least seen a movie where they've done target shooting. What is the true or accepted value when you're shooting at a target? It's the bullseye, right? And how accurate you are is defined by how close you are to that bullseye. For example, this person shoots a bullet goes in the bullseye, so they'd be very accurate. One thing you'll notice about my definition of accuracy that's a little bit different from other people is, whoops, there's a typo here. They said expected and it's accepted. Accuracy is how close a measurement is to an accepted value. Lots of books will say the word true instead of using the word accepted. In my mind, you should never use the word true. You should always use the word accepted. The reason for this is a minor point, but you never want to not allow for the possibility that you're right and the rest of the world is wrong. Therefore, I always use the term accepted value instead of true value. Accuracy, mathematically in the laboratory, is measured using a quantity known as percent error. You will use percent error in about 50% of the labs you conduct in this class. Therefore, I am now telling it to you, and you need to be able to remember it for the rest of your life. Percent error is measurement minus accepted divided by accepted, and then if it's a percent, what are you going to multiply by? 100. So percent error is the absolute value of, see, those are absolute value signs right there, right? Absolute value signs. Percent error is the absolute value of the measurement minus accepted divided by accepted times 100. Let's work a quick example. For example, compound X has a density of 19.3 grams. In a lab, a student measured the density to be 18.9 grams. What is the percent error? So percent error is the measurement. In this case, the student made a measurement of 18.9 grams. The accepted value is 19.3 grams divided by the accepted value of 19.3 grams times 100. Let's take a look at our sig figs as we're working along here. First thing we have to do is our subtraction step. So we look at that, and we've got 19.3 minus 18.9. And when we do that, that gives us a negative 0.4. But we're taking the absolute value, right? So that negative doesn't matter. However, look what happens to our sig figs. As a result of this subtraction step, we've been reduced to 1 sig fig up on top. So now we do the math. 0.4 divided by 19.3 times 100 gives us a calculator lie of 0, 7, 2, 5, etc. So we do our sig figs. We have 1 sig fig here, 3 sig figs here. So we can only have 1 sig fig in our answer. So our answer winds up being 2%. The student's error was 2%. Chemistry's easy. Life is hard, right? You definitely don't need Perry to help you out of this one. Why don't you write down Perry? P-E-R-R-Y. Everybody write down Perry. Okay, so we've defined accuracy. Now we want to define a closely related quantity known as precision. Precision is how close a group of repeated measurements are together. If I was to go back to the bullseye example, and I'm doing some target practice, to have high precision, I want all my shots to be close together. For example, I fire 3 bullets, and while I'm not very accurate, I got all 3 of my bullets fairly close together, so I have good precision. Of course, we want ideally I want good precision and good accuracy. So I'd want all 3 of my shots in my bullseye and close together. So how do we measure precision in the chemistry lab? We measure precision in the chemistry lab by using a quantity known as standard deviation. Conceptually, standard deviation is how close, on average, a group of repeated measurements how close on average a group of repeated measurements are to the average. Now, I don't mean to be mean about this. That was a joke. But I'm trying to get you into a statistics mode. Thank you. Make sure you try the salad bar, or I'll be here all week. All right, so let's look at the standard deviation conceptually here using a really easy example. All right, let's take a look at a really simple example here. I've given a quiz to a group of 10 students, and their scores are as follows. So what is the standard deviation for this group of students? First of all, remember our standard deviation is how close our group of students are to the average. So the first thing we'd want to do is we'd want to figure out what the average is of this group of students. In case you've forgotten how to take the average, remember the average is the sum of the measurements divided by the number of measurements. And when I add all these up, 12 5 times is 60, plus 8 5 times is 40, so I wind up with 100 divided by 10 measurements is 10. So the average of my group of measurements here is 10. My standard deviation is going to be how close my measurements are on average to the average. So let's do that. Let's see, how close are each one of my measurements to the average? Well, I have an average of 10. So my first measurement up here is 2 away from the average. My second measurement's 2 away from the average. My next measurement's 2 away from the average, right? 12 minus 10 is 2, 12 minus 10 is 2, 12 minus 10 is 2. So each of those is 2 away from the average. Same here for 8. 8 is 2 away from 10. And if I took the average of these numbers right here, I would find that on average, each student is within 2 of the average. And that conceptually is what the standard deviation is. Now, some of these scores were 2 above the average, right? My 12s were 2 greater than the average. My 8s were 2 below the average. So we would say that our standard deviation was +2 or -2 from the average. Conceptually, that's what the standard deviation is. Mathematically, it's going to be a little bit more complicated. It's going to be complicated by the presence of these negative signs. You're in agreement with me that just looking at this little chart we hear that our grades are within ±2 of the average. However, if I averaged this column outright, what would I get? If I added all these 2's and -2's together and then divided by 10, what would I wind up with? I'd wind up with 0, right? Because half are +2's and half are -2's. Therefore, I have to come up with a way of dealing with measurements that are less than the average. And that's why the standard deviation's formula is a little bit more interesting than a straight. All right, here is the formula for standard deviation. Looks really cool, right? It looks like something the prop guy would throw up on the blackboard in the background for a movie Mad Scientist lab here. But really, this formula, for all its highfalutin fanciness, is really pretty straightforward. First of all, this is a square root sign, right? Then we see this Greek letter E here. And actually it's epsilon, but it stands for sum, right? Actually it's sigma, isn't it? I don't know my Greek letters. But it stands for sum, right? Summation of a series from the first measurement all the way through to the last measurement. And what is it you're summing? You're summing up all these quantities right here. This x right here with a hat over it, in math, x with a hat over it is a fancy way of talking about the average or the mean of a group of numbers. And then this x sub I is each one of your measurements. So what this sum here is telling you is to take your average and minus each one of those, each one of your measurements from the average, and then square it and then add all those things together. Then divide by your number of measurements minus 1. N is your number of measurements here. If we were in statistics class, I'd go all Braveheart on you and tell you you're measuring your degrees of freedom. Where n is your number of measurements. And then finally, you're going to take your square root sign. So the formula looks bad, and right now you're probably not convinced that it's any easier, but let's work through it very simply on our own here. All right, let's clean up our data here a little bit. All right, so here we're back with our student sample data. Let's take the standard deviation of it. The first thing our problem tells us to do is it tells us to subtract each measurement from the mean. That's what that x hat minus x sub I is telling you to do. So we're going to take our average and subtract each measurement from it. So 10 minus 12 is negative 2. 10 minus 12 is negative 2. 10 minus 12 is negative 2. 10 minus 8 is 2. 10 minus 8 is 2. 10 minus negative 12 is negative 2. 10 minus 8 is 2. 10 minus 8 is 2. 10 minus 12 is negative 2. And 10 minus 8 is 2. So now what I've done is I've done the first part of my formula, and I've taken each measurement and subtracted it from the average. And if I was working the standard deviation at home, I would set up tables like this. Otherwise, your data tends to get lost, confused, and jumbled. So I've now created a column where I've subtracted every measurement from the average, or every measurement from the average, and I've wound up with these. The next part of the formula tells you you're going to square it. Squared, right? The purpose of squaring this measurement here is to get rid of those negative signs, right? Because you square a negative and it always winds up positive. So now we're going to square our measurements. Negative 2 squared is 4. Negative 2 squared is 4. 4. 4, 4. 4. 4, 4. 4. 4. And I sound like I'm playing the world's best game of golf here. So I've squared all my differences and wound up with 4. Now the next thing our standard deviation formula tells us to do is it says sum of the differences squared. So I'm going to add all my squares together. I'm going to add all these numbers together. And when I do that, since I have 10 of them, I wind up with 40. The next thing I'm told to do by my standard deviation formula is I'm told to take the sum of these squares and divide by my number of measurements minus 1. In this experiment, I have 10 measurements, right? I have 10 students, so I have 10 measurements here. So I have 10 minus 1, which, yes, I know is 9, but I wanted to make clear I was doing it. And then 40, right? We just determined that this quantity right here is equal to 40. Then, what's the next thing our standard deviation formula tells us to do? The next thing our standard deviation formula tells us to do is it tells us to take the square root. Why are we taking the square root? To undo the squaring effect, right? We squared our measurements to get rid of those negative signs, and that's not really fair, right? So we have to undo that squaring. So we're going to undo the squaring. By taking the square root. So I'm going to take the square root of the quantity 40 minus 40 divided by 9. And I'm square rooting the whole thing, right? (40 divided by 9). And when I do that, my calculator tells me these programs are great until they're not. It tells me second square root answer close equals. It tells me that my answer is 2 plus or minus 2.108185. And that's what my calculator tells me the standard deviation is. Now, what about standard deviation in sig figs? You can't deviate in something you don't measure. Therefore, here is your rule for standard deviation in sig figs. Trying to come up with a different color for it. The least place value in your average is the least place value in your standard deviation. What I mean by that is if I'm only capable of measuring something to the ones place, then I can only report a standard deviation to the ones place. Right? The standard deviation and your average are going to share the same least place value. So even though my calculator gives me all this, I'm going to do some rounding, and my standard deviation would be plus or minus 2. Because the least place value in my average is the 1, so the least place value in my standard deviations is going to be the 1s. Chemistry's easy, life is hard. So easy, even Doofenshmirtz could do it. Write down Doofenshmirtz. D-O-O-F-E-N-S-H-M-I-R-T-Z. Doofenshmirtz. In addition to standard deviation, there's one other statistical quantity that I really love, and that quantity is known as relative standard deviation.
What are you talking about?
And relative standard deviation is simply your standard deviation expressed as a percent of your average. Relative standard deviation is your standard deviation divided by your average times 100. So it takes your standard deviation and expresses it as a percent of your average. For our model here, your relative standard deviation would be plus or minus 2 divided by 10, which is your average, times 100, or your standard deviation would be plus or minus 20%, right? See how mentally saying that you have a standard deviation of, or relative standard deviation of plus or minus 20% sounds a whole lot different to you mentally than saying a standard deviation of plus or minus 2. And because we're used to thinking of in percents, I always like to use relative standard deviation just because it clicks with my brain a little bit more. Why don't you write down Candace? There's ain't no party like a Candace party. Everybody write down Candace. C-A-N-D-A-C-E. All right, that's it for this lecture. Beep.